Welcome to Basic Electronics Class 8. So we have already discussed the current voltage characteristics of a PN junction diode. So today we will discuss the capacitance of PN junction. Okay. So before we discuss the capacitance of a PN junction, let us get acquainted with two terms. The first one is majority carriers. So these are basically the carriers that dominate inside the material. So majority carriers are basically electrons for N-type semiconductors and holes for P-type semiconductors. Okay, so these are carriers that are available in plenty inside the device or inside the material, and these are carriers that dominate inside a material. Similarly, on the other side of majority carriers, we have minority carriers. Okay, these are carriers that are available in limited numbers inside the material. Example, electrons in p-type semiconductors and holes in n-type semiconductors. So in p-type semiconductors, electrons are available in a limited quantities. So they are known as minority carriers in n-type semiconductor. Similarly, in p-type semiconductor, in n-type semiconductor, the holes are available in limited quantities. So in p-type semiconductor, holes are the minority carriers. Similarly, in p-type semiconductor, electrons are available in limited quantities. So electrons in p-type semiconductor are the minority carriers. Okay. And we have seen earlier that the minority carriers can actually be derived by the following equation from the law of mass action. So in n-type semiconductor, p are the holes are the minority carriers. So holes in case of n-type semiconductor are basically given by Ni square divided by Nd. This is for n-type semiconductors. And for p-type semiconductor, electrons are the minority carriers, and this electron concentration is given by Ni square divided by Na. This is for p-type semiconductors. Okay, so I hope it is clear to you that what are minority carriers. So now we'll move to defining capacitance of a p-n junction. So there are two types of capacitance that affects a p-n junction. One is known as the depletion capacitance, and another is known as the diffusion capacitance. So let us understand what depletion capacitance basically is. So let us consider a p-n junction diode which is connected to a AC voltage source. Let us call this voltage source as VAC, and just as before, this side of the or the part of the depletion region on the P side of the junction contains accumulation of negative charge here, and the side of the or the part of the depletion region at the inside of the junction contains accumulation of positive charge here. Okay, now we know that whenever the diode goes from 0 voltage to forward bias, the depletion region decreases, which means the accumulated charge basically decreases. Now again, when the diode goes from 0 bias to reverse bias, the depletion width basically increases, which means the accumulated charge increases. So if we put an AC voltage source here, which basically makes the diode go from forward bias to reverse bias, and then again to forward bias, and then again to reverse bias in a cyclic way. Okay, if this happens, that during the positive part of the cycle the diode is going to forward bias, and during the negative part of the cycle the diode is going to reverse bias, and then again during the positive part of the cycle the diode is going to forward bias. So if this happens, this charge that is accumulated in the depletion region must also change. For example, during the positive half cycle when the diode is actually in forward bias, this depletion charge, the magnitude of the depletion charge would decrease. Then again, when the diode goes to reverse bias, this magnitude of the depletion charge would increase. And then again, when the diode goes to forward bias, the magnitude of the depletion charge would decrease. So in this way, as the AC voltage changes, the depletion thickness would actually change, and this results in change of total stored charge. So as the AC voltage is changing, the stored charge at the depletion region is also changing. So this is basically a capacitor like behavior. Okay, in a capacitor we know that whenever we apply a voltage source, or the charge is stored in the capacitor, or let us say the capacitor follows this equation Q equal to CV. So whenever this voltage changes, the stored charge would also change. So the diode or the depletion region of the diode acts in a similar way, that whenever this AC voltage source is increasing, the forward bias is increasing, then the depletion charge would actually decrease because the width of the depletion region decreases. Similarly, when this diode is going to reverse bias during the negative half cycle of this AC source, the AC voltage is decreasing and becoming negative, so the depletion thickness is actually increasing, and so the stored charge in the depletion region is also increasing. So the stored charge in the depletion region is actually changing in response to the applied voltage. Okay, so let me write it here. Since the stored charge in the depletion region changes in response to a change in the applied voltage, this gives rise to a capacitor like behavior. Okay, this capacitance or this capacitor like behavior is modeled mathematically by defining the depletion capacitance. So the depletion capacitance is given by the formula C dep, this dep for depletion, equals to dq depletion dv, where this q depletion is basically the magnitude of the charge stored on each side of the depletion layer. So q dep is basically the magnitude of the charge stored in each side of the depletion layer. Okay, so this depletion capacitance is basically defined as C dep equal to dq dep dv. Okay, now let us understand what the diffusion capacitance is. To understand this, let us again consider this PN junction which is connected to this AC voltage source. Now we know that when this okay, let us actually, instead of this AC voltage source, let us actually consider right now a DC voltage source which is connected to this PN junction here. Now we know that when this voltage source forward biases this PN junction, the diffusion rate of electrons from the N side to the P side increases, and the diffusion rate of holes from the P side to the N side also increases, and this is what gives rise to a current across this PN junction. So just as I discussed before, that exactly at the PN junction, the main component of the current is the diffusion current. The diffusion current basically increases exponentially with the applied voltage, or the rate of diffusion of electrons from the N side to the P side, and the rate of diffusion of holes from the P side to the N side increases exponentially with the applied voltage, and that is why the current in forward bias situation actually increases exponentially with the applied voltage. This thing we already discussed earlier. Now, since the rate of diffusion of electrons from this N side to P side actually increases with the applied voltage, and since the rate of diffusion of holes from the P side to the N side actually increases with the applied voltage, this builds up excess concentration of holes at this N side and excess concentration of electrons at the P side. Let me repeat this again. Since the rate of diffusion of electrons from this N side to the P side increases exponentially with the applied voltage, a concentration of excess electrons builds up at the N side just after the junction, or just after the depletion region, right outside the depletion region. And since the rate of diffusion of holes from the P side to the N side increases exponentially with the applied voltage, and excess concentration of holes actually builds up here at the N side just outside the depletion region. Okay, so there is an in forward bias condition, there is an excess concentration of electrons in the P side, and there is an excess concentration of holes in the N side. Okay, so this builds up excess minority carrier concentration just outside the depletion region. So if I draw a graph of minority carrier concentration, this would basically look like this. So at the depletion region there are no carriers. Okay, so right outside the depletion region, so this is the x direction, this is the boundary where the depletion region ends, and this is basically P0, which is basically the equilibrium concentration. Let me write it here. Equilibrium minority carrier in inside. Okay, so P0 is basically Ni square divided by Nd, just as we discussed, where Nd is basically the donor concentration in the inside. Okay, now I repeat again that because due to the application of external forward bias voltage source, the rate of diffusion of holes from the P side to the N side have increased. This builds up some excess minority carrier concentration at the P side, at the inside. Okay, so excess holes in the inside. So if I draw the graph here, it would basically look like this. This is the graph of P, which are the holes or which are the minority carrier concentration in the inside, and just outside the depletion region this excess minority carrier concentration builds up. Okay, this is the equilibrium minority carrier concentration here. This line defines the equilibrium minority carrier concentration, and due to forward bias excess minority carrier concentration have built up. So this is basically the excess minority carrier concentration. Okay, and as we gradually move away from the junction, this excess minority carrier concentration generally is nullified, and far away from the junction the excess minority carrier concentration actually coincides or becomes equal to this equilibrium minority carrier concentration. Similarly, in the P side also there is an excess minority carrier concentration or excess concentration of electrons. So let us assume that this is our equilibrium. So this is our equilibrium minority carrier concentration in the P side. So equilibrium minority carrier concentration in P side. Now again, since due to forward bias the rate of diffusion of electrons from the N side to the P side have basically increased, this builds up excess concentration of electrons at the P side just outside the junction. Okay, so if we were to draw the concentration of electrons just outside the junction, we would basically get a graph like this. Okay, so this is N. Okay, so just outside this depletion region, so this is where the depletion region basically ends. Just outside the depletion region we have an excess accumulation, or we have a larger number of minority carriers which are electrons in the P side, and as we gradually move away from the depletion region the excess minority carrier concentration gradually gets nullified, and far away from the junction everything is in equilibrium, and the excess minority carrier concentration actually coincides with the equilibrium minority carrier concentration. Okay, so this is what happens during forward bias, which I have drawn in blue color. If this junction on the other hand is reverse biased, what happens in the reverse bias scenario, let me just remind you that during the reverse bias, the potential barrier at the junction basically increases, so the electrons uh, find it more difficult to diffuse towards the p side. Okay, so electrons find it more difficult to diffuse from the n side to the p side, and holes find it more difficult to diffuse from p side to the n side. Okay, so that is why, since the electrons find it more difficult to diffuse from the n side to the p side, this means enough diffusion of electrons is not happening from the n side to the p side. Okay, or diffusion rate of electrons from the n side to the p side is less than before. So this basically reduces the minority carrier concentration near the junction. So during reverse bias, the minority carrier concentration near the junction reduces compared to the equilibrium value. So okay, so this is the excess or graph for excess minority carrier concentration during reverse bias. Okay, so just outside the depletion region, this is actually for holes, which are basically again minority carriers in the n side. So just outside the depletion region, the concentration of holes is actually 0, because no holes are actually diffusing from the p side to the n side. Okay, during reverse bias, the potential barrier has increased, so no holes are actually diffusing from the p side to the n side. So just outside the junction, the concentration of holes in the n side is actually 0. And then as we gradually move away from the junction, or as we gradually move away from the depletion region, the concentration of minority carriers gradually increases, and far away from the junction, this minority carrier concentration coincides with the equilibrium value. Yeah. Similarly, for the p side also, during reverse bias, the diffusion of electrons from the n side to the p side reduces due to increase in potential barrier. So this minority carrier concentration just outside the depletion region is actually 0. Okay, it is actually less than before, it is actually 0 now, because the diffusion rate of electrons has drastically reduced. Okay, the diffusion rate has approximately become 0. So the minority carrier concentration just outside the depletion region is 0, like the previous case. And as we gradually move away from the depletion region, this minority carrier concentration actually coincides with the equilibrium value. So these two graphs are for reverse bias, these red colored graphs. Okay, and this blue colored graphs here, or blue colored curves here, are for forward bias. Okay, now note that every time the voltage changes, or every time this diode goes from forward bias to reverse bias, the excess minority carrier concentration must change. Okay, so for example, during forward bias, excess minority carriers are built up just outside the depletion region. Now as this diode gradually goes from forward bias to zero bias condition, in case I apply a AC voltage source, as the diode gradually goes from forward bias to zero bias condition, this minority carrier concentration, or the excess buildup of minority carriers just outside this depletion region, must actually be removed. Okay, so I repeat again that during forward bias, this excess minority carrier concentration has actually built up just outside the depletion region. Now as the diode goes from forward bias to zero bias condition, this excess minority carrier concentration, the total excess minority carrier concentration, which is basically proportional to the area under this curve, the total excess minority carrier concentration must be removed before the diode can actually go to zero bias condition. And then when the diode gradually moves from zero bias condition to reverse bias condition, the total minority carrier concentration at the junction must be or the total minority carrier concentration just outside the depletion region must be removed. Okay, so the minority carrier concentration during the reverse bias profile basically looks like these two graphs over here. So as the diode gradually moves from the zero bias condition to the reverse bias condition, the minority carrier concentration proportional to the again area under this curve should actually be removed. Okay, so that is to say that as the diode gradually moves from forward bias to zero bias and then to reverse bias, the total accumulated excess minority carrier concentration just outside the depletion region must change before the diode can actually switch its behavior. Okay, so this again is analogous to the behavior of a capacitor, just as I stated that in a capacitor with change in voltage the total charge also changes. So here also, as the diode gradually moves from forward bias to zero bias condition, as the voltage gradually decreases across the diode, the this minority carrier concentration must actually be removed. This excess minority carrier concentration or the accumulated minority carriers just outside the junction must actually be removed. Okay, so this is equivalent to charge removal actually. Okay, again when the diode goes from zero bias condition to the reverse bias condition, the minority carriers just outside the depletion region must be removed. Okay, or the minority carriers just outside the depletion region must be depleted. So these minority carriers must be depleted before the diode can actually behave like a reverse biased situation, or before the diode behavior coincides with that of the reverse bias situation. So as the voltage across the diode is gradually changing, the excess minority carriers or the excess charge due to the minority carriers must also change before the diode can actually uh, behave, or before the diode can actually accommodate the behavior of the biased situation. Okay, so this is equivalent to the behavior of a capacitor, and since this minority carrier concentration actually builds up due to diffusion of electrons from the n side to the p side and due to diffusion of holes from the p side to the n side, the capacitance that arises from this charge is known as the diffusion capacitance. So so we define this diffusion capacitance C diff as dq diff dv, where q diff is basically the excess minority carrier concentration or the magnitude of the excess uh, magnitude of the charge. So let me just delete it here. So q diff is the magnitude of the charge due to accumulation of excess minority carriers just outside the depletion region. So this minority carrier or this diffusion capacitance is basically given by this formula C diff equals to dq diff dv. Now the question is, how does this depletion and diffusion capacitance basically affect the characteristics of the diode? So the answer is that they don't affect the characteristics of the diode in when we apply a DC voltage source, but when we are applying a time varying voltage, uh, they affect the behavior of the diode in this way, that let us say that the voltage is varying very slowly, and so this depletion charge and this minority carrier concentration is getting enough time to actually adjust with the applied voltage. Okay, so if the voltage is changing very slowly, the depletion charge and the diffusion charge, or the total depletion width and the charge due to the minority carriers are getting enough time to adjust or to change in response with the applied voltage, then this diode behavior doesn't change much. On the other hand, if the applied voltage varies so fast that this depletion charge and this diffusion charge cannot change in response to the applied voltage, then this diode acts as a short circuit, just like a capacitor. So in a capacitor, if we change the voltage at a slower rate, the capacitor basically behaves as an open circuit. Okay, and if the applied voltage is changed very fast, then the capacitor basically behaves like a short circuit. In this case also, if the applied voltage changes very fast such that the depletion charge and the diffusion charge cannot get enough time to adjust or to get modified in response with the applied voltage, then this diode basically behaves as a short circuit. So we'll see the AC model or the small signal model of the diode after a few minutes, but before that, let us discuss another thing. So we have seen that the IV characteristics of a diode resemble somewhat like this. So you may ask the question that both in forward and reverse bias, this diode current is increasing exponentially with the applied voltage. So here also the diode current is increasing exponentially with the applied voltage, and in the reverse bias also, after a point of time, this diode current is increasing very fast with the applied voltage. So you may naturally ask the question that what is the difference between the forward bias and the reverse bias case. So the answer is that normally during the forward bias, so this is the forward bias characteristics, and this quarter is the reverse bias characteristics. So generally the diode current in forward bias actually increases sharply after a cut-in voltage, which we call V gamma actually. Okay, so V gamma is generally known as the cut-in voltage, and this is the voltage after which the diode current increases sharply with voltage in forward bias. Okay, so after approximately the forward bias voltage reaches V gamma, this diode current increases sharply with the forward bias voltage, and this V gamma is approximately it approximately lies in the range of 0.3 to 0.8 volts. So V gamma lies in the range of 0.3 to 0.8 volts. Actually, it is 0.3 volts for germanium diodes, and it is approximately 0.7 volts for silicon diodes. Okay. On the other hand, during the reverse bias voltage, the voltage after which the current increases sharply with reverse bias voltage, this voltage is known as the breakdown voltage. This voltage is basically known as the breakdown voltage, and the difference is that this breakdown voltage is actually lesser than minus 5 volts generally. So this breakdown voltage is generally less than minus 5 volts. Okay, so it can be minus 6 volts, minus 7 volts, minus 8 volts, minus 10 volts. And the difference, another difference between the forward bias and reverse bias characteristics is that this voltage V gamma cannot be controlled to a large extent. Generally, this V gamma is constant for a particular type of diode. For example, for germanium diodes, this V gamma is approximately 0.3 volts, and generally this 0.3 volt for V gamma cannot be modified much. Okay, for silicon diodes, V gamma is approximately constant at 0.7 volts. So this V gamma cannot be modified actually. So this V gamma generally depends on material parameters and which materials make up the diode. The breakdown voltage, on the other hand, can be modified to a large extent by actually manipulating the doping concentration and by other methods actually. So this breakdown voltage of the reverse bias diode can actually be modified to a large extent actually. Okay, and the third difference is that after breakdown, this increase in current with reverse bias voltage is actually much steeper than the increase in current during the forward bias situation after you cross the voltage V gamma. So the reverse bias characteristics after breakdown is actually much steeper compared to this forward bias characteristics after reaching the voltage V gamma. So these are basically the differences between the forward bias and the reverse bias situation. I hope it is clear to all of you. Now we are discussing the diffusion capacitance and the depletion capacitance, and we stressed on the fact that these generally affect the behavior of the diode when the voltage across the diode is basically changing. So if the applied voltage is very fast, or the applied voltage changes very fast, then this minority carriers and the depletion region cannot change in response to the applied voltage, then the diode basically acts as a short circuit. Okay, on the other hand, if the applied voltage is varying slowly such that the depletion width and the minority carrier concentration can actually change in response to the applied voltage, then the diode actually behaves like a normal diode. Okay, so before we see the actual models for varying voltage, let us actually study the switching behavior of diodes. Okay, so let us assume that a diode is basically connected to the ground. So this is the symbol of a diode. I don't remember if I have actually shown it earlier. This is the symbol of a diode, and this arrow basically indicates that in which direction current can flow. So as we have seen that in the forward bias situation, the current always flows from the P side to the N side. Okay, if you don't remember it, let me show you the forward bias situation briefly. So this is basically the forward bias situation of a diode where the voltage is applied with the positive terminal connected to the P side and this negative terminal here which is connected to the N side, and the current would flow in this direction actually. Okay, so the current is basically flowing from the P side to the N side. On the other hand, if the voltage direction is reversed, like in the reverse bias situation, in this scenario, so in reverse bias situation, as we noted that before breakdown no current can flow. So basically in the reverse bias situation, current cannot actually flow from the N side to the P side. So this flow is basically prohibited before breakdown. Okay, so current cannot flow in the reverse bias situation, and current can flow in the forward bias situation from P side to the N side. So this basically means that in a diode, current only flows from the P side to the N side provided that the diode is not in the breakdown regime. So this arrow basically indicates the direction in which current can flow. So this side of the arrow is basically P side, and this side of the arrow is basically N side. So current can actually flow in this direction, and that is how this arrow is made to denote the direction of flow of current. Okay, so this diode is actually connected to the ground through two voltage sources and resistors also. So this terminal here is basically a switch. So I can either connect this diode to this voltage VR through this switch, or I can either connect this diode to this voltage VF through this by rotating this switch basically. Okay, and this voltage VF, when the diode is connected through this path, this voltage VF basically forward biases the diode, and the diode is connected to the voltage VF through this resistor RF. And when the diode is basically connected to this path here, this voltage source VR basically reverse biases this diode, and VR is connected through the resistor RR. Now initially let us assume that the diode is connected to the voltage source VF through this resistor RA. Okay, so initially this switch is closed, so current would flow through this path like that. Okay, so initially this diode is connected to this voltage source VF. Now at t equal to 0, okay, at t equal to 0, this switch is basically connected, this switch is rotated and connected to this voltage source VR. Okay, so initially since the diode is connected to this voltage source VF, so the forward biased current would flow. So before the time t equal to 0, the forward biased current is flowing across the diode, and this axis basically is the time axis, and this is basically the current through the diode I. So before t equal to 0, the forward biased current is flowing through the diode, so this is IF, which is the forward biased current here. Okay, and then at t equal to 0, the switch is rotated, so the diode basically goes from forward bias to reverse bias. Okay, I repeat again that initially before t equal to 0, the diode was connected to the forward biasing voltage source VF through this resistor RF, so this part of the connection was closed, and at t equal to 0, this switch is rotated, so this path opens up and this path closes, and so at t equal to 0, this diode is connected to the voltage source VR through this resistor here RR. Okay, now immediately when this switch is rotated and this diode moves from forward bias to the reverse bias state, the current does not go to 0, because during the forward bias state there is excess accumulation of minority carriers on each side of the junction outside the depletion region, just as we discussed that during forward bias there is accumulation of excess minority carriers just outside the depletion region, and in reverse bias all these minority carriers are depleted. Okay, so during forward bias there is an deposition of excess minority carriers which must be removed before the diode can actually behave like a reverse bias diode. Okay, when at t equal to 0, the switch is rotated and the diode suddenly goes from forward bias to reverse bias state, the minority carrier concentration must be removed before the diode can actually behave as a reverse bias diode. In addition, the depletion width must also change before the diode can behave as if the diode is in reverse bias state. So immediately when the switch is actually rotated and the diode is connected from voltage source Vf to the voltage source Vr, the current immediately does not go to 0, but the current actually reverses its direction, and this reverse bias current is given by IR approximately equal to VR divided by RR. Okay, and this current, this negative current is actually necessary to remove all these excess minority carriers accumulated at the junction during the forward bias state and to gradually change the depletion width. Okay, I repeat again that in forward bias state there was accumulation of excess minority carriers just outside the junction. If you don't remember, let me show you the graph. So in the forward bias situation, there was accumulation of excess minority carriers just outside the depletion region, and these minority carriers needs to be removed before the diode can actually behave like a reverse bias diode. So this current IR is actually necessary to remove these excess minority carriers from the junction, and this current IR is also necessary to actually change the depletion width. Okay, so to change the depletion width, excess depletion charge must be supplied, and this current IR does this job also. So this current IR supplies depletion charge to widen the depletion region in reverse bias mode, and this current IR also removes these excess minority carriers that accumulates in the depletion region. Okay, so this current basically removes these excess minority carriers. The major function of this current is actually to remove these excess minority carriers at the junction. So this current basically remains almost constant to the value IR given by approximately VR divided by IR, as long as the excess minority carriers is stored at the junction. As this excess minority carrier concentration gradually decays towards 0, this current actually starts to reduce, and this current gradually goes to approximately 0 when all the minority carriers near the junction have actually been depleted. Okay, this time frame over which the reverse bias current across the diode remains constant to a large magnitude, this time frame is known as the storage time. This time frame is the time up to which the excess minority carriers is stored at the junction. So I repeat again that the storage time is basically the time up to which the excess minority carriers is stored with the junction, or there is accumulation of excess minority carriers at the junction. As the excess minority carriers becomes equivalent, or the excess minority carriers becomes equal to the equilibrium minority carrier concentration, this current actually starts to decrease, and when this minority carrier concentration are depleted and the minority carrier concentration just outside the depletion region becomes approximately 0, this current also goes to 0, and then the diode behaves like a reverse bias diode in steady state. Okay, so this time over which this reverse bias current is almost constant and large, this time is basically called storage time, and during the storage time there is excess minority carrier concentration just outside the depletion region. After the storage time is over, the minority carrier concentration just outside the depletion region becomes equivalent to the equilibrium minority carrier concentration, and after the storage time starts the fall time. The fall time basically starts from here up to the point at which the reverse bias current actually falls by this large reverse bias current actually decreases by 90%. So this value is approximately 0.R1 IR. So this value is approximately 0.1 IR, where IR is given by approximately VR divided by RR. Okay, so after the storage time starts the fall time, and fall time is the approximate time over which the minority carrier concentration or all the minority carrier concentration goes from the equilibrium value to near zero value. Okay, so basically the turn off time of the diode. Okay, so the turn off time of the diode is basically the time required to bring the diode from forward bias state to reverse bias state, and this is equal to the storage time plus the fall time. So this turn off time is the approximate time required to bring the diode from forward biased state to reverse bias state. Okay, so whenever the diode voltage polarity is changed suddenly, the diode doesn't go from forward bias to reverse bias state immediately, or the diode does not go from the forward bias state to the steady state reverse bias state immediately, but the diode takes some time to go from the forward bias state to the reverse bias state, and this time is basically the time frame over which these minority carriers or the accumulation of excess minority carriers just outside the depletion region is removed to zero. Okay, so the turn off time is the approximate time that the diode takes to go from the forward bias state to reverse bias state. Similarly, we also have the turn on time, which is basically the sum of the storage time plus the rise time, and storage time is basically the same as before. It is basically the time required to build up minority carrier concentration to the equilibrium value from zero value, and then rise time is basically the time required to build up the excess accumulation of minority carrier concentration just outside the depletion region. So I am not going to explain this. This is basically the same as before, or this is basically the same as this equation over here, so please learn this yourself from the book. Okay, so I repeat again that whenever the diode is whenever the voltage across the diode reverses its polarity, the diode does not go from a forward bias state to a reverse bias state immediately, or the diode does not go from a reverse bias state to a forward bias state immediately, but it takes some time to go from one state to another, and the time the diode takes to go from one state to another is basically the time that is taken to for the time that is taken for the minority carriers concentration to go from that state to equilibrium value, and from equilibrium value to the other state. Okay, so let us do up to here today. Thank you everyone.